Okay. Thank you very much. It's a great pleasure, it's great joy to lecture in front of such a big crowd, so enthusiastic as you are. As I'm just watching this, I realize maybe there might be some distortion in the images we'll see when it arises. I also noticed that I made a first mistake since it is not 14 but 15 December. Okay. Let's talk about art of mathematics, and in the talk I will mix several stories together. My personal story and evolution as a mathematician and the problems I worked with, but also the story of some mathematical adventures, but also the story of how we work as mathematicians. And because mathematics, more or less, in the, at least in the form that we know nowadays, more or less was invented by ancient Greeks, let us start with the Greek mathematicians. And these I like to think of the 5 most famous mathematicians from the ancient times. Each of them can be considered as symbol of some important aspect of mathematics. So, first, on the left, Thales. Thales reminds us that mathematics and philosophy are so closely related to each other. Sometimes Thales is called the first philosopher, sometimes the first mathematician, and of course, he is a very prominent figure in both. Next, Pythagoras. Pythagoras, of course, is the most popular for non-mathematicians because there is a famous theorem, but also it's a symbol of the idea that there are mysteries to solve in the nature around us, and that we have, some of these mysteries are found in special relations between numbers. Then comes Euclid. Euclid is the symbol of the power of the written transmission, the book, and all that this can do to disseminate knowledge and to preserve it. It is said that the book of Euclid was the most edited non-religious treatise in all history. And, of course, recently the book of Euclid was still used as part of the curricula. There is no other science in which things remain true as long. Mathematics, something that you prove remains true for thousands of years. In all other fields, you have to change much more frequently. Next in line is Archimedes. Archimedes would be a symbol of the mathematical genius, the one who sees better and further than the other ones. He is the one whose face is on the Fields Medal. And last in line, Eratosthenes. Eratosthenes could be a symbol of the ability of mathematics to change our view of the world and to go and learn things about our world that our common sense and intuition is not sufficient to get. Here is the most famous of Eratosthenes' achievements. Eratosthenes was both geographer and mathematician, and in a famous calculation, he used some particularity of some well. There was a well in Sienne such that the sun would shine exactly at the vertical certain day in the year. He used this particularity and some clever mathematics, clever but not difficult, to measure the Earth. And he obtained a measurement which was about correct, up to maybe 2% of error. And it's remarkable to think that 2,000 years ago and more, people at least the Greek mathematicians, they knew the size of the Earth with great accuracy. Some example, as I said, of the fact that mathematics changes the vision that you have of the world. I remember reading about this achievement of Eratosthenes when I was a kid, in one of these books of science explained to kids, and it remained a vivid memory. What you read as a kid has a lot of influence on you because it is engraved very hard in your brain, sometimes without you noticing. And it is very often that people are influenced all their life by things that they read when they are young. As a famous example, the great mathematician Alan Turing, all his life was influenced by a book that he read when he was 10 years old. And there are a number of other examples. When I was 10 years, I'm not sure what I read, but I remember I was watching this movie, Donald in Math Magic Land. I found it was really super. Well, I tell you, it is not deep mathematics, but it can make a big impression on kids. In Donald in Math Magic Land, it was insisting on mathematics, especially in relation with the arts, with two major problems: how to construct the musical scale, a problem which is, whose solution is attributed to Pythagoras in its first version. You know, because the various frequencies of the strings on the guitar or whatever, you would like them to be definite fractions, and you ask which fraction should it be, etc. And there are some subtleties. And the other was the golden ratio and its would-be appearance in many works of art. I found this fascinating, and later I would understand that these two problems, people talk about them a bit too much, in the case of golden ratio, far too much, and that golden ratio certainly does not deserve to be so much popular, even though it is important. But it was very well done in terms of pedagogy, because it was hooking kids with some things that are easy to relate with, like music or visual arts. Actually, nowadays, the theme of the interface between mathematics and art is extremely popular, and you find even journals devoted to this. And this, of course, is an interesting and important topic. I'll come back to it later at the end of the talk, but right now I will emphasize on the fact that mathematics in itself is some kind of art, and that there is output from mathematics which very much relates to artistic notions, even though we will not think of it naturally as some piece of art. And first, to begin with, let us recall that art in the first place is about representing the world or giving a certain interpretation, a representation of things in the world. And it is remarkable that many objects of nature can be represented with basic concepts of mathematics and with useful, deep concepts of mathematics, sometimes with very simple geometrical shapes. Also that mathematics, and here we are back to the Pythagoras idea, allows you to represent any kinds of signal, be it, for instance, a song here, in terms of numbers, in terms of functions. And this is extremely powerful. It gives some kind of universal representation of things around us. Universal in the sense that you can convert some reality into some collections of objects which eventually boil down to numbers and relations between numbers, but then which we may think of as logical objects, forgetting about the numbers behind. Let us also recall that many of the laws governing nature can be expressed in mathematical terms. This was the idea conveyed in this cartoon, which I took from some comic blog, whose title was How Scientists See the World. And of course, in this picture, the intention is clear. Whatever the scene, however natural it is and so on, you may find behind it lots of mathematical equations, which are like abstract representations. First comment is that if you really want to draw the list, of course there are many, many more equations than there are in this. You would need probably a full book like this to write them. Second comment is that a remarkable feature of nature around us is that in many cases we can isolate some of these features or some of these phenomena or some of these equations and study them, forgetting for a while about the rest, and then get some understanding by combining the knowledge which we gain from these various parts. This is a remarkable thing about the nature of the world, allowing us to studying it in depth. Let us then note that mathematics is not only useful to analyze the world, but also to make it, to do it. And as an example, here is this building, kind of weird building, the Fondation Louis Vuitton, which was inaugurated in Paris last year. It was a big international buzz. And it was made by famous architect Frank Gehry. But this building does not seem to be mathematical in any way, because you cannot see any symmetry, for sure no golden ratio, and so on. However, it relies deeply on mathematics, because with such an extraordinary building, if you just build it like you trying this and that, you are sure that it will collapse. You need a prior building to entirely build it in the digital world, to compute the stresses and the force and make sure that it really stands. And a couple of decades ago, it would have been impossible to make this building because the software aiding the architects was not up to the task. It needed to be perfected. Of course, the software does not make everything. There were also a certain number of patents on certain devices used to construct the Fondation. But it needed also the computing power and the mathematical equations, modeling and reproducing this reality before it even exists. And also in this direction, but remaining in the virtual world, here is an image from one of the arguably most mathematical movies ever made. This is Gravity, and one of the remarkable things about Gravity is that essentially it is all done virtually. The only thing which is true in the movie are the faces of the actors, almost. All the rest is computed by means of algorithms and mathematics. And again, it needed several years of development of the digital technology before it was possible to produce this movie. So again, an example of the power of mathematics. Also illustrating the fact that mathematics has some poetic value. Poetic in the etymological sense, which is about creating some kind of new world, inspired from the world that we are used to, but different in certain respects. In this case, the main difference is that gravity was removed. And you see, once you create the mathematical world, you may change the laws of nature. And this is more and more used in the animated industry. So this illustrates the ability of nature to create this world, kind of intermediate between our world and a completely different world, somewhat in between. And that, as I was saying, can be considered as some kind of poetry. Actually, there is a nice sentence by Léopold Sédar Senghor saying that mathematics is the poetry of sciences. It was the title of a lecture which I gave some time ago in Belgium. Mathematics and poetry can be actually compared in several respects. The first is this creation goal of mathematics and poetry. The second is the extreme importance of constraint in both arts, if I may say, poetry being extremely self-constrained art, as well as mathematics. And the third is the fact that mathematicians, as poets, believe in the power of words. Word as something which not only has a certain meaning, but also conveys some meaning, helps the understanding or the evocation. And it's the conviction of mathematicians that you need to choose the right concepts and define them in order for future generations to have a good understanding of the concepts, to transmit, and so on. It happened sometimes by the way that poets used mathematical words to enhance the poetry, provide some atmosphere. This was the case in particular of Lautréamont. Now, having said that mathematics is poetic, one should also say that it's very useful and that the job of mathematician is very much praised nowadays. And look at this beautiful ranking, which was from 6 years ago, when Wall Street Journal decided to rank all the jobs that they could think of, including criteria such as happiness, social status, whatever, many, many criteria, and they put #1 mathematician. Of course, these kind of rankings can be argued, but still, certainly there is some good element of truth behind. Notice also how many science jobs there are in the first rows of this ranking. And when you give a talk about the nature of mathematics, something you quickly learn is that whenever you insist on mathematics being useful, you immediately need to balance by saying that mathematics is also beautiful, and that is the next slide. If you forget to say that mathematics is beautiful, there is somebody who will tell you, you know, yes, it's useful mathematics, but the most important is that it's beautiful, and vice versa. If you insist on the beauty of mathematics, somebody will tell you, you know, the important is that it's useful. So let's talk about beauty in mathematics. On the left is Aristotle, and in this quote, he describes beauty using the words like order, commensurability, and precision. And you really have the impression that he's talking about mathematics. And indeed, in the sequel of the text, he says that this is why mathematics is such beautiful art. More than 2,000 years later, Henri Poincaré, the most famous French mathematician, the most famous French scientist of his time, would speak of the profounder beauty coming from the harmonious order of the parts, summarizing the notion of beauty which is most popular among mathematicians, when several concepts come together as if they were fit for each other in a certain proof which is like a construction, an architecture of concepts and arguments. And this is very important for mathematicians, not just as something which is good, something which is nice, this notion of beauty, but also as something which helps them in their work. It's important that in the mathematical teaching, one is exposed at a young age to this idea that there is some beautiful element in mathematics. And that you can say, wow, this is great or something. And it can be done on many different fields. Let me say that when I was a teenager, my favorite subject was this one, geometry of triangle. Maybe 14 years old or so. So I read and reread this book. Geometry of triangle is nice because it's full of miracles. Sometimes you have 3 lines that come together at a single point. Sometimes you have 4 different points which are on the same line, etc. And yet you learn that there are no miracles and that you can explain all these beautiful coincidences. And you can replace all these beautiful coincidences by beautiful explanations. And wow, now I understand. Let me also mention that geometry of triangle has really no use at all. and that there is no research in this field any longer, and that in everyday life it really has no use. But, you know, I trained my skills in setting up proofs with this many years ago. And later it became my job to set up proofs that may be sometimes 100 pages long on tricky concepts of mathematical physics. You have to start at some point. So starting on 10-line proofs of geometrical concepts is good. And let me also say that after I received Fields Medal, together with another French mathematician, French-Vietnamese mathematician, Ngo, and both of us were meeting some members of the parliament in France after that, and they asked what we thought about the curriculum in mathematics, and immediately Ngo said, elementary geometry is the best, it was my favorite subject at school, etc. And then I said, yes, it was the best, exactly the same, even though neither him nor me are working in this field nowadays. Because when you are in high school, the first purpose of the course of mathematics is to make you understand what is a mathematical proof and to make you find some mathematical proofs. All the rest is details. Now, let's go on to explain how sometimes some elementary or less elementary mathematical problems could change the world and have applications in our daily lives. And I told you about Eratosthenes and measuring the Earth, and this has no daily application. But still, it was a change in the world. Let us now consider some other fundamental problem, which is not about measuring distances, but about measuring time. How does one measure time? Most of the methods in ancient times were based on water or liquid, which is flowing in a regular manner. It is not so long ago that it was discovered that, in a very surprising way, at about the time of Archimedes, there were constructions of mechanical clocks in some parts of Greece. But apparently, the knowledge of this was lost for 1,000 years. And mechanical clocks started again in the medieval times. And they were perfected and perfected during hundreds of years, but somehow around the 16th century or something like that, the technology arrived at some kind of peak, and it was very difficult to improve. It was based on clever mechanisms, you know, which organize and unfold in a rather regular manner. And the best accuracy was something like 1%, which in the precision, 1% looks good, but it is like maybe 10 minutes in a day, it's not so good. So then came some changes. And one of the most important events was this one, when people started to study pendulum. So Galileo, around 1600 or something, studies the motion of pendulum. And we all know a pendulum is something like this, and if there is no friction, it oscillates in a regular way. And Galileo discovered that there is more regularity than that. That the period of oscillation is independent of the mass of the pendulum. Only depends on the length of the pendulum. And so that is rather easy to reproduce in some sense. Later in the 17th century, it would be put into equations, like the second derivative of the angle, theta with double dot, is proportional to the negative of the sine of the angle. And this equation in general you cannot solve. You cannot compute the period, for instance, but you can see already from the equation that it doesn't depend on the mass, because the constant only depends on is the ratio of the strength of gravity, g, by the length of the pendulum. It's the most important example of differential equation which you solve and explain and comment and study. And you see, at the beginning, it is about predicting the period of the pendulum. So knowing the time, compute the properties of the pendulum. And then at some point there was a change of order, and people had the idea of, let us do the reverse. Instead of using the measurement of time to predict the pendulum, let us use the oscillation of the pendulum to measure the time. And so there was the idea of doing a clock based on pendulum oscillations. But then, it's not so easy. It's not so easy, and several problems are under the way. One of the problems being that this period, this time, is only true for very small oscillations. And the length of not the length, but the time it takes for the pendulum to oscillate depends on the amplitude. So if it has a lot of energy, the time is not the same as if there is just a small energy. How to make this as constant as possible? And this was solved by Huygens in these days. And it was remarkable calculations using the most advanced mathematics of the time, using differential calculus and geometry. And he asked the following question. Imagine that instead of making my pendulum free like this, I put a constraint on the pendulum. Like here with my hand, I'm constraining the pendulum. And so this changes the trajectory of the pendulum, and this may change also the period. And he asked, is there a possibility to find the guide on the pendulum such that this constrained motion would satisfy the property of tautochromy, which is that the periods would be independent of the energy. And he found that there is just one shape doing the job. And this is the cycloid. Cycloid is a curve like this. You take a wheel and you mark one point here in red, and then you make the wheel roll, and you see the trajectory of the red point. That's the cycloid. Here I reverse the figure to make it look like what we will use for the pendulum. So imagine that your pendulum is attached there at the apex of the cycloid, and then it's constrained by these bits of cycloid. Then the trajectory of the pendulum, of the end of the pendulum will also be a cycloid. And, most importantly, the time period will be independent of the energy. Exactly independent. So this added a lot of invariance in the problem. And it was one of the core principles of the clock that Huygens built. And the accuracy was something like 100 times better than what was done before. These clocks are still preserved. Now, this was getting into quite precise measurement of time. And it was, as you saw, solved by a real mathematical computation. There is no way that a clockmaker could have found this cycloid form just by trial and error. It really required some mathematical skill and asking the right abstract question. Let's also say that this was the start of a big technological evolution and innovation about the measurement of time, which would culminate for mechanical clocks in the 18th century with the famous clock of Harrison that had an amazing accuracy such that when it was put in a boat and the boat went for a trip of several months, when it was back, it was only a few seconds of time difference. And the clock of Harrison was so precise that it allowed people at sea, the captain, to measure the longitude, a very old and famous problem about going on the sea, how to measure the longitude, and the solution was by looking at the difference between the local time and the time of the where the ship took off, and the time of the city that you come from. In the same way as when we travel, say from Mexico to Paris, there is a difference between our time and the local time in the city that we arrive, and this is jet lag. By measuring the local jet lag of the clock, you know where you are. This was remarkable and very important. Knowing the longitude allowed you to avoid the places which were known to be very dangerous for storms. It has also mentioned that nowadays, with very different techniques, physicists, experimenters, they know how to build, and the most accurate of them are in Paris, clocks which have an accuracy of 10 to the minus 18. Clocks which are so precise that on the whole time span of the universe, maybe they have a few seconds of inaccuracy, and which are so precise that if you move the clock from here to here, the measurement of time will change, just because of the strength of gravity being slightly different here and here. But in those days, the Harrison achievement, of course, was spectacular. Now, at the same time as Harrison was perfecting his clock, he worked on this for decades and decades. At the same time, in France, Buffon was working on probability. And it was part of a fascinating story, understanding the laws of chance. This is a picture for the famous experiment of the Buffon needle. You take some wood floor like this, with some lines, and you take a needle whose length is exactly the same as the distance between two consecutive lines. And you throw the needle on the floor many, many times. And you ask, which is the proportion of times when the needle will meet one of the lines? Okay. And the answer of Buffon is that its proportion of these times is approximately 2 over pi, so nearly 2 over 3. And it's an experiment you can check and do at home. what is remarkable is that if you try to do it in the most random possible way, it will work even better. This is with the laws of chance. Usually, if you want to have a precise result in some experiment, you tune the instruments very precisely so that there is no source of perturbation. But here, it works better if you perturb it in all kinds of possible ways. Sometimes you throw the needle in the air, sometimes you spin it, whatever. You do whatever you do. And you will not escape this 2 over pi. And it was one of these laws expressing the fact that chance is governed by some rules which you cannot escape, even though chance is something that a priori is unpredictable. In this story about the laws of chance, a most important episode occurred in the middle of the 18th century with Abraham de Moivre. De Moivre was a French emigrated to Great Britain to avoid religious persecution. And he discovered this curve, which now is called the Gauss curve, but which could very well be called the De Moivre curve. And its equation is something like exponential minus x squared, and De Moivre discovered that it governs the errors to the ideal statistics. What does it mean? Well, take a coin and throw it in the air, and then you record if it will be head or tails. And of course, with one coin, you cannot predict if it will be head or tails. But if you throw it in the air many, many times, it will be roughly 50-50. 50% heads, 50% tails. And now you ask, what is the deviation with respect to this ideal statistics? And the answer is that the deviation is unpredictable, but that it obeys some statistical law. And there is a very large probability that it is very small, and this corresponds to the bulk of this bell shape, and a very small probability that it is very large, and this corresponds to the tails of the curve. Now, this was a remarkable achievement, and once again, showing that there is some law which you cannot escape, even though here it is a game of chance. It took about 80 years before the intuition of De Moivre could be proven in all generality, or nearly. And this was done by the French mathematician Laplace. And what Laplace showed is that it's not just for head and tails, it is for whichever experiment which you repeat many, many times in independent manner, the deviation of the observed proportion with respect to the ideal statistics will follow a bell curve, a universal curve. This, for sure, is one of the most important theorems in all mathematics. And it appears kind of everywhere. You find even this curve in many situations that don't seem to be related to chance. It was put in a very eloquent way by Francis Galton a few decades later. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of frequency of error. The law would have been personified by the Greeks and deified if they had known of it. It is a supreme law of unreason. And it's very well said. This is one of the things that mathematicians love. When you have something universal which appears in many, many situations, giving some ordering, some better understanding of many features in the world. And as Poincaré said it someday, mathematics is the art of giving the same name two different things. Let's see one example of application, of consequence of this Gaussian law, which again changed the world. And it was about measuring something which was, let's say, something related to the microscopic world. With Eratosthenes, it was to go to very large amounts, very large distances, and measure the Earth. But at the beginning of the 20th century, what scientists did was measuring things that are very, very small, invisible, or, for instance, more precisely, to prove that the world around us is made of many, many molecules, so small that they cannot be seen, and to compute how many molecules there are, for instance, in glass like this, which is filled of air. It was Jean Perrin, around 1910 or so, who wrote the book which achieved to convince everybody of the existence of these atoms. And the book, the interpretations of the experiments, were making a big use of statistics and of the idea of the Gaussian distribution, of this universal bell shape. It was based on the analysis, among other experiments, of Brownian motion. So, Brownian motion is you take a small particle, very small, but still you can see it with your eyes or with a microscope. And you put it in some water, for instance. And you observe it, and it will start to be agitated by kind of random motions. And the interpretation of this was that this particle, which is very small but still visible, is constantly hit by many, many invisible tiny particles, like molecules. And if you look at the particle, it is hit at the same time on all directions, and so typically there will not be much motion, because if I am hit by particles at the same time in all directions, I just don't move. But from time to time there is an error to the ideal statistics, which is that all particles will collide you in all directions simultaneously. Sometimes, for some reason, some particles hit you many times in the same direction. It is an error in the statistical sense, and then you go in that direction. And if you ask about the typical statistics of this motion, well, it should be Gaussian, because it is about errors made in many, many repeated experiments of collisions with tiny particles. And so you can compute the statistics of the position of particles, the statistic of the position of 2 particles, 3 particles, etc., by developing this idea. The experiment, which is analyzed here, and was done by Theodor Svedberg, you have a big box filled with water, and a number of particles which you put in the box and which are randomly moving. And at a regular time interval, you focus on a special place, a special subdomain in your big water tank. And you count how many particles you can see in there. And these are some results of the experiment. At some point there was just 1 particle in the subdomain. At some other point 2 particles, then 0 particles, 0 again, etc. And you have this long list of observations. And from this you compute some statistics, like probability that the particle will come back to the box, etc. And you compare it. You compare it to the ideal statistics which you compute from the Gauss model. And then from this and some model of molecular motion, you deduce the characteristics of the molecular matter. And for instance, how many particles typically there are in your fluid, in some unit of fluid. None of these numbers was greater than 6 in this long list of observations. And still, from the analysis of this sequence, people were able to find the Avogadro number, which tells you how many molecules in one mole of, in a certain standard unit of gas. It was a triumph for statistics. Again, there is no way experimenter could have deduced this number. It needed sophisticated mathematical model. And in the end, the reward was a change in the vision of our world, because it is only by comparing the different values of the Avogadro number predicted by the various experiments that people get convinced of the existence of atoms. Once again, it was application of advanced concepts from mathematics and here physics, which had enabled a complete change in the vision of the world that we live in. Let us also say that Jean Perrin was not only a great scientist who received Nobel Prize, but also very much involved in developing mathematical institutions and thinking a lot about the contact between science and society. Jean Perrin, for instance, founded the Discovery Palace, which was very important for advertising sciences for generations of kids. And he was co-founder of CNRS, which is the biggest science institution in France nowadays. In French institutions, of course, it's like in every country, you need strong institutions so that the science can be developed. It's not just about good scientists, it's also about good institutions where they can develop. And this is the moment where I come back to my story. This is the institution where I did my higher studies, École Normale Supérieure. So École Normale Supérieure was founded roughly at the time of the Revolution. It had ups and downs and so on, but it established itself as a very strong point for sciences and literature also. In mathematics, it is particularly strong. If you look around the world, for the records of Fields medals, where did the people do their higher studies, you see that there are two places in the world which are much higher than all the rest in terms of the result. One is University of Princeton, and the other is École Normale Supérieure in Paris. But I was not aware of this when I entered École Normale Supérieure. I just thought, let's continue to do mathematics, it's interesting, so let us go on and study. I had no idea of the job that I wanted to do, and I realized on the first day at school that I was going to be paid. I even did not think about it before. And I realized another thing, that you have to choose. When you do higher studies in mathematics, at the beginning you have the impression that, of course, mathematics is a big subject. But you don't realize that later you will have to find a sub-subject to develop. When you enter mathematics school, maybe your family thinks that you're a bit special. When you tell them that now you will choose a specialization inside mathematics, they think that this is the end. So you don't tell them that you will have to choose later a sub-subfield to specialize, and later a sub-sub-subfield, because they would, not understand what is happening to you. But it's a principle. You have to specialize, and later you will be able to develop and do more things. In my case, I specialized in this, partial differential equations. It was difficult to predict, since when I entered École Normale Supérieure, my strong subject was algebra, rather than analysis or differential equations. And also what was weird is that I specialized in mathematical physics related to partial differential equations, even though I was not so good in physics. For sure, for my physics teachers, it would have been a big shock if they had known that I would become a specialist of mathematical physics. Each of these equations represents an important phenomenon going on in the world. And it can be the evolution of fluids, it can be the evolution of the state of one atom, it can be the evolution of a whole galaxy, or it can be the evolution of gas, as described by this equation, and this was the one I worked on. Let me also say that when my PhD advisor first wrote down the equation for me and explained to me that it would occupy me for the next 3 years, I thought that maybe it was time to change subject, you know. But in the end, it worked real fine, and I fell in love with the equation, Boltzmann equation, after the start of my PhD, and worked on it for many years. And let's talk a bit about Boltzmann. And this was like 12 years after I studied to work on the equation, and the picture was taken in 2006, as I was one of the invited lecturers in a conference which was held in the memory of Boltzmann, 100 years after his death. This conference took place in Vienna, and I knew that he was buried there. So after having worked for so long on his equation, I considered him as part of family, you know, and so I went to pay a tribute in the cemetery. This grave is very famous because on it is engraved the formula of the entropy, Boltzmann's most famous formula, which reads S equals K log W. S is the entropy or notion of disorder in a gas. And the idea of Boltzmann was that when you observe a gas, because it is of microscopic nature, made of many, many tiny molecules, we cannot know the microscopic structure of the gas. All that we can know are some macroscopic average features. And so there remains an awful lot of possibilities in the microscopic structure of the gas, and this huge number of possibilities, we'll call it W. And then the size of this number of possibilities, which is a logarithm, will tell us about the inner complexity of the gas, the inner disorder, the many configurations, the size of the unknown that is possible. This notion of entropy, the notion of entropy existed before Boltzmann. It was associated with thermodynamics. But now, with the work of Boltzmann, it was taking a whole different nature, a statistical nature. And then, there was another key discovery by Boltzmann, that it is related to the arrow of time. So this is where maybe the two stories which I told you about mastering time and mastering statistics, they come together in the work of Boltzmann. And Boltzmann went even so far as to say that, by definition, time flows in the direction where entropy spontaneously increases, when there are random phenomena. The idea that the gas becomes more and more disordered, and that typically any system in which there are random phenomena at work will have its entropy increase. So something which is fundamental for our interaction with the world and the notion of time at our scale. And also something which explains the world. For instance, you see here on the picture, I put some molecules in the right half of the box. They are well ordered because they are all on the right and none on the left. And if you let these particles now free to evolve as they wish, experience shows that they will flow everywhere. We like to interpret this as the fact that there is the vacuum sucking in the particles. But Boltzmann tells us, you know, it's true that the particles go where there was vacuum, but it has nothing to do with the force, it's just the statistics. and the fact that the gas will prefer a configuration which is more disordered, in which particles can be anywhere, right or left. So it was a fundamental progress in the understanding of the evolution of the matter around us. And all this is somehow encoded in this formula, S is K log W. So, a very deep, important formula. Let me, by the way, tell you the detail of my encounter with Boltzmann. When I arrived in the cemetery, I discovered that it would be a problem to find the grave because the cemetery was so huge. And I think I have to find a map because there are these famous people buried there, so there has to be a map where they are located. So I asked to some family, do you know where I can find a map of the cemetery? And they told me, no map, who are you looking for? What do I answer? Boltzmann. And then what do they answer? S equals K log W. Secret password in the sect, you know. So, the work of Boltzmann was a preliminary to the work done later in 20th century by people to discover, to prove the microscopic nature of the world. And they pushed the theory extremely far, assuming that gas is made of tiny molecules which bump on each other. And they used this, and they also used the entropy formula, but they also used the equation here, the Boltzmann equation, which allows you, assuming that you have statistical nature of matter, which allows you to predict the evolution of these statistics. So it was an extraordinary progress. And they did some computations. For instance, Boltzmann showed that if you look at the variation of entropy, it's always in a negative, which means that the entropy goes up and up, never down, spontaneously. And he even gave a formula for the entropy increase. It's beautiful, clever proof, by the way. Now, with this, immediately you see that many questions arise that did not arise before. In mathematics, as in all sciences, the more you know, and the more there are questions. So the number of open problems is increasing with time, not decreasing. As soon as you know that the entropy is increasing, then you ask, up to where? And you think maybe there is some maximum of the entropy which will be reached, or almost reached. Maybe I can predict this maximum. It will be universal law. And then you ask, but then, which is the maximum? So it's a mathematical exercise. You sit down and you compute distribution of particles which has a maximum entropy. For instance, the distribution of velocities in particles. And you compute, and you find that, again, it is your good old Gaussian law, which has the maximum of entropy. So beautiful. You see here, we found a link between the law of errors, coin tossing, and the gas, even though it seems these are different things. This is something mathematicians or theoretical physicists like so much. Also because when you have a bridge between several fields, like gas and random coin tossing, it gives you progress on both sides. And in particular, some people understood later that you can use the entropy to give a new proof of that theorem of Laplace, that the law of errors is a Gaussian distribution. Big conceptual progress. But then, there are other questions now that arise. If the gas converges to Gaussian because of the increase of entropy, how fast will this convergence be? In the 80s, the mathematician Carlo Cerciniani, one of the main specialists of Boltzmann equation, stated a conjecture according to which the variation of entropy should be at least proportional to the difference of the entropy between present state and maximal entropy. And this was one of the subjects on which I worked on my PhD. See here that physics subject gives a lot of inspiration for mathematicians. We know what is the production of entropy, it's a mathematical formula. We know what is the difference of entropy, it can be computed mathematically. Then it becomes a mathematical problem with implication in physics. So, in '97, I was visiting in Pavia the mathematician Giuseppe Toscani. And he suggested that we work on this problem. I had met Toscani a few months before, and I had shown him a big mistake in one of his papers. This was a good way to become friends. So he invited me to Pavia, where he was a professor, and he told me, you know, I have an idea to solve the Chladni conjecture, but it's a bit of a crazy idea, and we will do this, so add some noise and some diffusion and compute how it depends on the noise and then blah blah blah. Okay, and he explained me, and then since he was the head of the department, he had no time for research, so he rushed to some administrative meeting, and as I was PhD student, I had all my time, so I sat down and I worked for hours. And I discovered that the idea was complete crap. And that it could not work. And, you know, I got this calculation, I think, but of course it will never work. But, in the computations to check the idea, there was something fishy. Caught my eye, and there was, you know, combining together several terms in computation, you ended up with a beautiful perfect square, which was not expected. And I thought, this is too beautiful to be useless. The perfect square is the one here that you see, so with framed in red. And indeed, this was like an identity, and the identity was the start of the proof in the end. So we used this with Toscani to make a big progress in the conjecture, and I used it again several years later to solve it completely. So with this I was learning two important lessons. First lesson, when you embark on a project, it's maybe a good idea to start with a bad idea. Start with an idea that is completely wrong, but you start something, you try something. And then you may have some ideas that will lead to the right idea. If you just wait until you have the perfect idea, you may wait forever. You should try, and something will come out. And second lesson is that when it's beautiful, it may be useful. It's something that mathematicians are deeply convinced of. We look for the beautiful relations, not just by pleasure, but because we are convinced these are the ones that will lead to the good results. And I worked on this field then for a number of years, in particular trying to understand the relaxation of a gas and the laws of evolution of the entropy. One of our main discoveries, together with my collaborator Laurent de Villette, was the fact that the increase of entropy, so the entropy production, is not so smooth as one could expect. Particularly when you take into account hydrodynamic phenomena arising in the Boltzmann equation. Look at the plot on the right. It is a plot in which what is drawn is not the entropy but the information, which is just the opposite of the entropy, so it will go down, and it's a logarithmic plot. And it's the upper curve which gives you the decrease of the information. And you see that the decay is not uniform. Sometimes fast, sometimes slow, and it corresponds to the fact that in certain situations, typically in a gas, there will be an alternance, some kind of oscillation between times in which the entropy production is strong and time in which entropy production is weak. Entropy production weak is not good news to study the trend to equilibrium. And so this was one of the effects which we studied as part of some more general theories about studying systems in which entropy production may be rather weak, and still you want to prove that there is convergence to equilibrium and control the speed. After this, I stopped working on the subject after writing a big memoir named Hypocoercivity, which was like a generalization of this, and let other people continue to study this and develop, as one should always do. And then change subject. It's a good thing in mathematics, you can change subject without having to change all your laboratory. And in particular worked on other problems more related to geometry, but again with a taste of entropy and Boltzmann. Here is the one which was most striking and which was developed through collaborations with Felix Otto or through work with John Lott, Carl Theodor Sturm. And the idea was to characterize geometric bounds on the so-called Ricci curvature. It's one popular notion of curvature, by studying the entropy and its evolution under some imposed law, which is not the same as the law of gases. And I often say this is how you would explain curvature to Boltzmann if he would come out of the grave. And to explain him what it means, a world which is curved in a positive way, a bit like a sphere, it's the following. You assume that you start from a gas with a certain statistical distribution at initial time, and you impose another distribution at final time, maybe 1 minute later. And you let the gas moving from the initial configuration to the final configuration, and the gas will do this in the most lazy way possible, that is by spending the least amount of energy. And all along you measure the Boltzmann entropy from initial time to final time. Initial is prescribed, final is prescribed. What will happen in between? If the curve is always concave, which is like this, it's the sure mark that you live in a space of non-negative curvature. No. I was telling you we like in mathematics to do connections between fields. And this was a beautiful example of connection between the problem in geometry, understand the curvature, and the problem in gas theory, understand the entropy. And actually this link led to progress in the understanding of entropy, but most importantly to progress in the understanding of curvature. Some problems which stood open in geometry for quite a long time were solved with these ideas. And beforehand it looked that it was just a problem in geometry, and then it was solved in the end by using statistics and entropy. And however, the equilibration problem caught me again later. How did this occur? Was by some chance, accident, anyway, together with my former student, Clément Mouot, we wanted to study a certain thing, and then in the process of doing so, we decided to switch and study some other phenomena which we thought we could study and overcome, even though it was not the equation we are familiar with. And this was a problem in which entropy production was not weak, entropy production was zero. And still you expect to get equilibration. And this is a phenomenon which is famous, for instance, in astrodynamics, because as noted by astronomer Lyndon Bell in the 60s, if you try to understand why galaxies are in some kind of statistical equilibrium, you cannot base this on entropy, because entropy production is so slow that you can neglect it. And so how to explain that there is this kind of statistical equilibrium? Lyndon Bell argued that there should be some violent relaxation, that nobody knows what it is, but which sounds cool. Violent relaxation, which is that it should equilibrate without entropy increase. And since this seemed very strange, he argued that it should be as in plasma physics. In plasma physics, a revolution arrived when Landau in the 40s had the idea of what is now called Landau damping. What is a plasma? Plasma is one of these systems that you see here. It's actually the fourth state of matter, as is often said. It's not gas, it's not liquid, it's not solid, it's plasma. Which means that the electrons are separated from the rest, and electrons are almost independent from the positive charges, and so they act like a kind of gas of electrons, repelling each other. And who is Landau? Landau is this guy here, legendary physicist, who got Nobel Prize, who wrote very influential treatises together with Lifshitz. Here you can see he doesn't look happy, it's normal. This is the mugshot when he was sent to jail. Because in those days in Russia, if you were, you know, speaking too loudly about certain things, and if in addition you were Jew, then you were in very bad shape. It was remarkable that he could be taken out of jail by the action of his colleagues. This was really very courageous. Anyway, Landau was out of jail and could continue his extraordinary work. And in the 40s, he published a paper which became legendary, in which he said, let's consider plasma, it was studied by this guy and this guy, but all their results are wrong. And in fact, the important thing in plasma is that there is some equilibration, some stabilization property. And he argued, doing some mathematical calculation, which was rather elaborate, that if you take a homogeneous plasma at equilibrium and perturb it a little bit, then spontaneously it should stabilize, even though there is no friction in the plasma. This was a big shock. We are used to the stabilizing action of friction, related with entropy increase and things like this. And for instance, you know, if I take something and I push it like this, the friction will prevent it from going too far. It's stabilizing action of friction. But in plasma there is no friction, no entropy production, and so it looked as a complete mystery when Landau said, you know, perturbation should dissipate spontaneously. This is called a Landau damping now, and it's very well used. And because the equation underlying plasma physics is the same as the equation underlying astrodynamics, at first order, Lynden-Bell argued that there was a similar phenomenon for galaxies. These things, the signification of Landau damping still triggers debates nowadays. And for instance, the popular interpretation which you find in many sources, I am convinced that it is the wrong one. Anyway, there was a controversy whether this Landau damping really would hold for very large times, even for gravitational interaction. Most importantly, in the Landau computation, he cheats by replacing the nonlinear equation by the linearized. Cheating is okay in general, as long as you have arguments to explain why you think you can cheat. But in this case, it's very difficult to argue why you would be able to cheat. And people, starting from Bacchus in 1960, have pointed out that it looked like there was an internal contradiction and that it was impossible to linearize, and so on. Whether there was really Landau damping for the nonlinear equation then was the subject of debate. Various people at various times gave various answers. Physicists, not sure, mathematicians were not sure, anyway. And so with Moore, we decided we could attack this problem. And then we started the normal activity of a mathematician, which is to just think and fail, and think again and fail again, and continue like this for a long time. Some people believe that science is like, you know, think very, very hard and then solve the problem, and after doing some experiments, but in reality, it's a much more complicated process. You see here, what did the author of this cartoon write? that you think, you accept the challenge, you do science, then everything breaks apart, what the hell, you start again, but no, somebody already had this idea, it doesn't work, you start again and obtain some amazing results, they turn out to be complete crap, then you wonder, what the hell, what is there, yes, makes no sense, makes sense. When you discover that something makes sense, you find that also somebody did it 50 years ago, so big mess. Big messy way. And from time to time, it works. The artist here made it for one person. But in fact, you have to imagine, because it's collective work. It's the same for many people, and they interact, and at the same time, all these are very complicated loops that come into action. And we went through this process with Clément, big mess, in which we made so many mistakes and met many people, and we thought we had understood and it was nothing, etc. And in the end, we did solve it. 2009, we proved that Landau damping does hold for perturbations of homogeneous equilibria for the nonlinear model, and under some technical conditions which I will not explain, but which are okay. In particular, gene stability condition was the condition that physicists were saying should be the right one. So, in some sense, we solved the problem. What was the result of this? First, a big paper, which is how you should share your results. In this case, this was a 180-page long paper proving just one theorem. And with some good, big old computations, like we like it. So, very happy. This result actually, together with the work on Boltzmann equation, is what got me the Fields Medal. So it was opportunity for a lot of public celebration and public sharing. Also, in some unusual ways, in this case, which I did not expect, but which were interesting. And for instance, this is a portrait which appeared in some cultural magazine, in which the journalist chose a title which was, "I am the Lady Gaga of mathematics." But why not? So, after that, I even made an appearance in fashion magazines. Not for long, just once. Because I hate these magazines that explain you how to dress, how to think, etc. And more importantly, it was an opportunity also for sharing with people with other scientists, for sharing, for instance, with physicists. If you are a mathematical physicist, after you've worked your problem through, you have to go back to the physicists and tell them, here is what I understood. And of course, you will not give them the 180-page long paper full of calculations. You have to explain which is a new insight. In this case, one of our main discoveries was that there was some deep link between three famous physics facts. One was this Landau damping. One was the Kolmogorov theorem on stability of integrable systems with perturbations. And roughly speaking, this theorem stated that some perturbed systems remain very well ordered without apparent constraint. It was an important theorem at some point in the struggle to understand whether the solar system is stable or not. Stability of solar system and stability of plasma are very different physical problems. But there is a common mathematical structure, and this we understood. And the third phenomenon was the plasma echo. Beautiful experiment from the 60s. You take a plasma at rest, you perturb it with some electric impulse, and then the electric field in the plasma will oscillate and damp to zero. Then you perturb it with another pulse, so there will be electric current again, and then go to zero. And then you do nothing and wait, and there will be an echo. spontaneously, at a later time, the electric field will go up and then down. This is the echo. And it reflects some of the paradoxical properties of plasma, but in particular the fact that the plasma reacts with delay. Some interactions are made in the plasma, but with some delay, and we understood that this delay was a key in the stability problem, and understanding, quantifying the delay. And of course, we also shared it and gave it to other mathematicians for developments. In science, when you have a new idea, you give the new idea to other people, not to preserve it and venerate it, you know, but to change it, to simplify it, to reinterpret it. And so our work was simplified, was adapted, etc. In particular, two researchers used it together with other ideas of their own to solve a problem in fluid mechanics which was more than 100 years old. You take a fluid which is two-dimensional and with a special velocity profile that is linear, as in this picture, the so-called Couette flow, and you ask whether it is stable, even if there is no viscosity. Perturb it a bit, you wait, does it converge to some stable equilibrium? And the problem is very tricky. And they proved that yes, under some conditions. And this was also a step for later a study which they made of the 2D and 3D stability for this Couette flow in, when the viscosity is very, very small. If there is a very small viscosity, which is the size of the perturbation that you are allowed, and still it will remain stable. So a number of progress, which came as consequence of our result, but also the addition of new beautiful ideas. Now, there are also some final ways in which you can solve, with which you can share the joy of the theorem. And this is by sharing not the result, but the history of the result. And all this complicated, messy story which was expressed by the cartoon before, with all the setbacks and all the difficulties and all the coups de théâtre. And this is what I did in a book which was published 3 years ago in France, in which I describe the story of this proof, like behind the scene, how is it when mathematicians work, and I describe it like kind of adventure novel, in which you have to make some big threat to overcome or something, but all completely true. And I put it also with all the atmosphere of the mathematician's life. So with all the big words that we use, and no explanation for the words, with the equations, and so I put these scores of equations inside the book to give the atmosphere. And I explain about all the details when you are when you are sitting late at night to overcome the problem, when you are desperate because it doesn't work, when you are joyful because it works, when you say something which turns out to be complete crap, when you encounter somebody, discuss, and it starts again, etc. So there is a famous quote by Stephen Hawking that every formula divides the number of readers of your popular book by 2. If it was true, there would have been only a few molecules of reader to buy my book, but instead it sold 100,000 copies or so, which shows that in the end, people are not only interested in knowing the result of our scientific discoveries, they are also very much interested in knowing about the battle, how it is, the adventurous life of the scientist. And also they're interested in the process of sharing. And let me conclude with the final, let me skip all this and jump directly to the final, the experiment which was done by artist Jean-Michel Alberola on the occasion of an exhibition devoted to mathematics. And his idea was, let us not represent the result of a mathematical work, let us represent the process of mathematical working and show the process of mathematical sharing between mathematicians. When we share as mathematicians, we explain proofs, we do computations to each other, and we like to do it on Blackboard. This is the absolute best technology which was never surpassed for transmitting mathematical ideas between mathematicians. And so he made this short movie about just me explaining the ideas, giving a seminar on one of these steps involving the physics of gas. And this was very popular short movie in this exhibition. Even though I'm so much used to Blackboard, it was a nice shock for me when I saw how good it looked. When you see, for instance, at times the chalk, there's this small, there is a bit of speck of dust of the chalk that goes out, goes in the light. Sometimes the Blackboard is well lit, sometimes it is not. Blackboard is good because also you can correct mistakes, you don't go too fast, you adapt to the understanding of the guy who are listening to you, etc. And in the end, in the end, you see something which has been used to convey ideas between specialists, but for the artist, it is also a work of art in itself. It goes into a tradition of representing some abstract concepts of, for instance, at some point, the photographer Man Ray did a lot of pictures of shots of mathematical equations in the form of geometric shapes, fascinated by the idea that these were objects used by human beings to communicate subtle abstract concepts from one to another. And so this, the work of Alberola, making a short movie on this, can be considered as tribute to two great inventions which were a company for mankind all throughout their progress: invention of writing and invention of mathematical formalism. Two inventions which were not natural, and it's clear our brain was not made for that, we were not selected for that, but which were an enormous tool to help mankind go beyond what common sense, oral tradition, and so on can provide. And with this, I will conclude and thank you for your attention.